Welcome. I'm Dr. Morton, and I'm going to cover Chapter 4 in this video. Okay, so here we are. This is Chapter 4, and you can see the idea or the concept here is we go from an idea to a truth table and then to logic equations, and from the logic equations we go to hardware. So this is what switching algebra allows us to do. It facilitates this transition. Now the truth is, most of these devices that we wind up with are going to be actually state machines, and we haven't gotten to that part yet. But every state machine, all the logic blocks in that state machine are made up of combinational logic, which is what we're learning now. Okay, so here are the learning objectives. I want you to be able to write out 3 of the key theorems for conversion, 3 of the key theorems for simplification. You need to be able to simplify a logic expression, maybe not to its ultimate smallest size, but you need to be able to at least take some steps. And finally, you need to be able to convert a simple two-layer and or logic expression to or and form, and vice versa. So that would mean conversion, and we'll talk about that. And then you need to be able to take a logic expression and take its inverse or to take its dual, and we'll talk about that. Okay, the glossary is right here, and you can see in the glossary that we have a bunch of terms, and as you hover over these terms, like in the other chapters, they're all their definitions pop up. So we want you to know about the switching algebra theorems, and we're going to cover those. What the definition of a logic expression, definition of a literal, definition of a term, and then the idea of conversion from one form to another, simplification, and we'll talk some about this concept of the order of precedence. Let me just hover over this for now. In fact, we'll raise this up. Order of precedence, a concept that differentiates that different operators have to be evaluated before other operations of lower order of precedence. So that in the expression 2 plus 4a, where a equals 3, the 4a multiplication must be done before the 2 is added. So the correct answer is 14 instead of 18. So you're familiar with order of precedence from your normal algebra activities. So it's not really a new concept, but as applied to logic expressions, it can be tricky. And one of the interesting things is that that logic expressions actually are commutative, which means you can do them in any order theoretically, and you get the same result. However, because they stole these terms from algebra, and in algebra they have order of precedence associated with them, we have to take that into consideration here in order to make them straightforward and clear. And so the only way to keep us completely out of trouble is to use a fair number of parentheses as we go through writing our logic expressions and converting them. Okay, we've talked about the advantage of having just true and false in our logic expressions, which means that a logic expression with 3 variables, those 3 variables can only have 8 possible values. So 8 possible combinations of values. So we can look at all possible values for expressions, and that allows us to do some comparison and some proofs that you cannot do in normal algebra, because a single variable has an infinite number of possible values, and therefore you would have to evaluate an infinite number, infinite times infinite for 3 variables, which of course is ridiculous. So you really cannot do this in normal algebra, but in switching algebra you usually can look at every possible value for a logic expression, and that allows you to compare both sides and see if they're always equal for every possible value, and if they are, you have just proven that expression. All right, here's the order of precedence for our functions. We talk about inversion. We should apply this first, and then if things are ANDed together, we should apply this next, and then if they're ORed, we should apply that. Pretty much just like you would signs, multiplication, and addition or subtraction in regular algebra. Okay, now we're going to talk about the 15 paired theorems. paired because they usually appear in two different forms, and the second form is typically the dual of the first form. Now, we haven't defined dual, but it's very similar to the inverse, and it's just that you change the operators, but you don't change the variables. Whereas in an inverse, you change both variables and operators. And we'll come to this in a minute. Okay, so we have grouped those into four groups. Okay, the first group are the trivial laws. We'll look at these. The next group are the simplification laws. This is where you can take a logic expression and simplify it. The third group is where we take a logic expression and use these theorems to convert it to the other canonical form. And then the final group are where we take the inverse of a logic expression or the dual of a logic expression. Now the dual, it shows up here in our table of theorems, but that's about the only place we use it these days. In the old days, it was a way to take a group that designed part of a system with negative logic and combine their design with a group that designed their system with positive logic. And you could take the dual of the negative logic group, and you would have then you could combine the final logic functions, and they should be able to work together. All right. So let's go through this. So the first group, we call these the trivial laws, and so the first ones are, and we've already looked at these in the last chapter, operations with the constant 0 and 1. So x ORed with 0 is just x. X ORed with 1 is always 1, because if any input is a 1, the output will be a 1. So it doesn't matter what x is. If you AND x with 1, you get x. But if you AND x with 0, you always get 0, because if either input's a 0, you get an output of a 0. In this case, one of the inputs is absolutely 0, so the output will be 0, even though we don't know what x is. Then we have what are called the idempotent laws, and that is, if you OR x with itself, you get x. If you AND x with itself, you get x. And here, notice, we're not using the little time sign anymore. We're just going to use typical algebra notation. The commutative rule shows that you can take the order in which you OR x and y. It doesn't matter. Same with ANDing. Complements. This is where we take the inverse of x and we OR it with its inverse. We always get 1, because one of these, if x is 0, then x prime is 1. If x is 1, then x prime is 0. So one of these is always going to be 1, and therefore x ORed with 1 is always going to be x, or x prime ORed with 1 is always going to be 1. X ORed with 1 is always going to be x. All right. In this case, we're ANDing x with its prime. Well, one of these is going to be 0, so something ANDed with 0 is always 0. And here, something ORed with 1 is always 1. So something ORed with 1 is 1. Something ANDed with 0 is always 0. And then we have the associative law. And this is just, we can group these however we want. Now, one thing to keep in mind is when we start using NAND gates and NOR gates, we have to be careful, because they're not associative. But regular OR gates and regular AND gates are. Here you have OR gates, and here you have AND gates. So you can AND y and z, and then you can AND the results of that with x, and that will give you the same as any of these results, or even all three of them. The double inverse. This becomes important for switching our functions into different forms. Notice if we take x prime and we invert x prime, we get back to x. So if you do two inversions, you haven't changed your function. Now, sometimes we'll do exactly that. We'll do two inversions, but we'll only partially expand it, and that gives us several different forms, all of which are exactly equal. All right, and then there is no dual to this. All right, now the simplification theorems. So the simplification theorems, there are 4 of these, but S4 we're not going to really talk about much, because it's called the consensus theorem, and it's a little confusing to use at this point in your journey. So we're going to save this for when we've already covered K-maps, and you can look at consensus terms in a K-map, and they're easy to see there, but they're hard to see without the K-map. And sometimes they're very tricky. So we're gonna leave this alone for now. But it is one way to eliminate a term. All right, so the remaining 3 simplification theorems, 1 combines terms, and we're going to use this extensively when we do K-maps. It's also what we use extensively to simplify truth tables. So we have 2 terms, x, y, x ANDed with y, and we OR that with x ANDed with y prime. So you see a y and a y prime, and both terms have x. In this case, since the y term changes, we can combine xy with xy prime and drop the y's and just have x. And that's also true here, where we're ANDing together x ORed with y and x ORed with y prime. That also just gives us x. This is the dual of this. This S2 is eliminate a literal. Now, let me just back up and define the concepts of variables, expressions, terms, literals. All right, so let me switch over here to my notes. So if we look at a logic expression like x, y, z prime plus x, w plus x prime, z prime, y prime, this whole thing we will call a logic expression. Now, it has 1, 2, 3 terms. This is an AND term, this is an AND term, and this is an AND term. And then there is actually one more. The whole expression itself you can think of as another term, but we don't usually call it that. We call it the expression. But that would be a OR gate with 1, 2, 3 inputs, generating a single output where we set this whole thing equal to F. So if we drew this out, we would actually write 3 AND gates So I'm going to put the little one here, 2 inputs, x and w. This one has 3 inputs, so that's this term. So we'll take this term, x, y, z prime, x, y, z prime, and then this one also has 3 inputs, 1, 2, 3, x prime, z prime, and y prime. They have 3 outputs, and we'll take all 3 of these outputs into one OR gate, and we'll give an output F. So we have 1, 2, 3 AND gates, 1 OR gate, so we have 4 gates, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inputs. And we generally, and 2 layers. This is the input layer. This is the output layer. The input layer has 3 gates, the output layer just has 1 gate, so we also have 3 layers. And we refer to these things as the cost of the hardware. The cost. It cost us 4 gates, 11 inputs, and 3 layers. Typically, a gate with an extra input, so our 2 input gate will probably be cheaper than our 3 input gate, and so forth. Take up less room on an integrated circuit, require less discrete chips if we were to implement it that way. It's what we did in the old days, but those days have passed. Mostly now, we'll take a dedicated integrated circuit, or maybe we'll just implement it with a microprocessor instead. All right, so that's the cost. Okay, back to our logic expression. So we have, make sure you can see this. So we have the whole thing's the expression. We have 1, 2, 3 terms. How many variables do we have here? Well, we have x in its non-prime and prime form. So that's one variable. We have a y variable. We have a w variable. And we have a z variable. So we have 4 different variables. W, x, y, and z in either their native or prime forms. So 4 variables. And how many literals do we have? This is a term you might not be familiar with. A literal is an appearance of a variable. So for instance, x appears here, here, and x prime there. So this variable appears 1, 2, 3 times, in this case, in the prime form. Each of these would be a literal. Y appears here and here, here non-primed, there primed. So that's 2 more literals. Z here, so that's another literal. And then W there, that's a literal. So we have 1, 2, 3, 4, 5, 6, 7, 8. 8 literals. So the cost of this function is determined by the number of gates, the number of layers, well, the number of inputs, and also the number of layers. Now, the number of layers doesn't necessarily directly add to the cost, but it does very directly impact how fast our network can work. If we have more layers, let's say we had another AND gate up here with some variables coming in instead of this X here, we would have to let these variables get through this gate. Maybe that has 10 nanosecond delay, another 10 nanosecond delay, and 10 nanoseconds here. So the worst case, say if this is X coming in here and this is W or something, then we might have as much as 30 nanoseconds from when X changes to when F would be readable, valid. And the more layers we have, the worse that gets. So we would always like to minimize the number of layers and have as few as possible. Since any logic expression can be implemented in 2 layers, we should be able to have no more than 2 layers in most cases. Now, the way it works out, we often have networks with many more layers than that, but for very different reasons, just for convenience of design and some other things. But it can get us into trouble on timing if we get too many gates, too many layers. Okay. All right, so that took care of our simplification theorems. Now I'm going to talk about these conversion laws. So this box here contains 2: the first distributive law and the second distributive law. And the first distributive law is just like normal algebra. We have x times y, the quantity y plus z, and we can write xy plus xz. We can also take xy plus xz, factor out the x, and get this: x times the quantity y plus z. So it works either direction. And we call that the first distributive law, or C1. C2 is the second distributive law, and it looks like this: x plus y times z equals x plus y quantity times x plus z quantity. And I guess I put an asterisk there, and I'm not sure why that's there. Oh, note, you can also think of the second distributive law. It could be x plus abc, and then you would have x plus a quantity times x plus b quantity times x plus c. So keep this in mind. This may very well show up on a test. Okay. And then we finally have the last one, and we call that the multiplying and factoring law, or C3. Now for this one, we have xy plus x prime z. So we need to have an x and an x prime, or a y and a y prime, or a z and a z prime. We have to have a variable. We have to have 2 literals, one primed and one non-primed, in these 2 representations to make this work. And then what we do is we take x plus z quantity times x prime plus y, and just like we have here. Okay, we also go the other direction. It's exactly the same thing. x plus y quantity times x prime plus z, and we get x prime y plus xz. Now notice here we switch the primes around. Doesn't matter as long as you keep them straight. And there's a little trick for doing this, so let me show you that. So let me switch here. So let's say we have x, y plus x prime z. Well, what we do is we draw a little line here, and we connect it to here, and we draw a little line on top here and connect it to the z. So now we know we're going to have, that's going to be equal to x here plus z quantity times the quantity x prime plus y. If we do it this way, we can do the same thing. We can do a little x, connect it to the y, the x prime, connect it to the z, and now we're going to write x, y plus x prime z. So it goes both ways. It's totally reversible. All right, so that is the multiplying and factoring, or the M&F. Multiplying and factoring, or C3. So in class, I'm going to refer to these as C1, C2, C3. I'm going to refer to these as S1, 2, and 3, and S4 for the consensus theorem when we get the K-maps. And I'm not going to really use these trivial laws, T1 through 6, but we'll talk about them occasionally. And I will talk about De Morgan's law as I1 and dual as I2. I won't use I1 and I2. I'll just use the word De Morgan's laws for I1, and that's where we generate the complete inverse of an expression. In the dual, which we will not use much at all in this course, we generate the dual, and we'll talk about the duals. Okay, so those are the theorems. Now, we can set up a little truth table here. Now notice our truth table it has some inputs, x, y, and z, and then we have a whole bunch of columns we've generated over here with different functions. This is the column for y anded with z. This is the column for x plus y, x ORed with y plus x ORed with the quantity y anded with z. And then here we have x plus y, or x ORed with y. Here we have x ORed with z. And then here we have these two entities ANDed together. So x ORed with y ANDed with the quantity x ORed with z. And what you'll notice is this represents x plus yz represents, say, the left-hand side of the second distributive law, and this represents the right-hand side of the second distributive law with the variables x, y, and z. And you'll notice that for all values of x, y, and z, and there are 8 possible combinations, all zeros, 0, 0, 1, and so forth, and finally 1, 1, 1, for all 8 of these possible combinations, the x plus yz column is always equal to the exact same value that the x plus y quantity times x plus z, or ANDed with x plus z quantity. So that proves that our relationship x plus yz equals x plus y quantity times x plus z. Now notice I'm going to use the words plus and times when I'm really meaning ORing and ANDing. And I do that because it's just awkward to do it any other way. So you have to fight through that initial confusion that we're not really adding things, we're not really multiplying anything. We are ORing with the plus, we are ANDing with the times. So the YZ is ANDed, and this X is ORed with the results of the YZ. Same thing here. We're generating 2 ORs here and ANDing them together, the results together, ANDing those results. And we just built this up by doing these extra columns. We don't have to have these extra columns, but it helps us compute this column. Okay. So here is the multiplying and factoring theorem. And you notice here's the left side, and here's the right side, or you can call them, you can switch left and right, it doesn't matter, but here are the two sides, and for all possible values of x, y, z, our three independent variables, the result is always identical. So we built these up by doing x, y here, x ANDed with y is this column, and then x prime ANDed with z is this column, and then we ORed these. So 0 ORed with 0 is 0, 0 ORed with 1 is 1, 0 ORed with 0 is 0, 1 ORed with 1 is 1, 0 ORed with 0 is 0, 0 ORed with 0 is 0, 1 ORed with 0 is 1, 1 ORed with 0 is 1. Over here, we have these two columns, and we're going to have to AND these together, like here. So x prime ORed with y gives us these values. X ORed with z gives us these values. And when we AND these, 1 ANDed with 0 is 0, 1 ANDed with 1 is 1, 1 ANDed with 0 is 0, 1 ANDed with 1 is 1, 0 ANDed with 1 is 0, 0 ANDed with 1 is 0, 1 ANDed with 1 is 1, and 1 ANDed with 1 is 1. And look, these two columns give us the exact same pattern. For every row, these always match, which proves for every possible value of x, y, and z, our two sides of our equation for our M&F theorem, our C3 theorem, if you will, are identical. And that proves the theorem. Again, can't do this in regular algebra because every variable has an infinite possible number of values. So not possible. But you can do that here. Okay, so the two canonical two-layer forms, which I briefly introduced in the last chapter in the video, here we have it. We call the SOP form in two layers. We have a set of AND gates in the input here. Let's see, I may have to shrink this down a little bit. So we can see this. So note, we have a bunch of AND gates. I put dots in here. There could be more AND gates. And then here's our one output OR gate. So in this case, we have 1, 2, 3 gates actually shown. 4, counting this one. 2 layers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inputs. So 4 gates, 11 inputs, 2 layers. And that's in SOP form. We are ORing together, summing up the multiplied results of our inputs here, are their products. So we're summing up products. So we call it a sum of products. So this is our sum term. These are the product terms. These are AND gates, hence multiplication. And this is an OR gate, hence addition. Again, it's not really addition, it's only ORing. It's not really multiplication, it's only ANDing. These are really AND terms, but we call them product terms. Probably just to confuse the students, I swear. It's sad, but that's how this has evolved. Not my fault. This was true before me. Okay, let me pop no, let's I don't want that. Let's see, what I do want is zoom back to 100. Okay. So all the gates, remember, they can have different inputs. They don't have to be, they just have to be in a real device. They have to be physically realizable. Well, what if you need more than you can physically realize? Well, then we'll add a layer, and we'll have AND gates, and then we'll have them go into another AND gate, and we can have as many rows as we want. It does increase the propagation delay times with the extra layers, or layer. All right. So we went through some things. Now I'm going to talk about how you switch from one form to another form. And I'm going to give you some hints for how to do that. Okay. So let's do that next. Okay, so I'm going to flip this around, I think. So we'll do a simple theorem. Let's say we have x, y plus x prime z. Let's convert this into so this currently is in sum of products form, SOP form. we have AND terms ORed together. So we have two AND gates and one output OR gate. Oh, sorry, you can't see it. Dang it. I don't know how we did that, but we did. Okay. So here's our SOP form. Now we want to convert that into a POS form. Well, so the first thing we would do is we notice that we have a variable x in both terms. Here it's x and here it's x prime. So that should immediately suggest C3, or the multiplying and factoring theorem. And so all we have to do then is we take this x and we connect it over with this c. We take this x prime and we connect it over with this y. And that equals x prime y plus y quantity times x plus z. Just like our C3 M&F theorem. Okay, so now it is in POS form. We have an OR gate here, an OR gate here, and we have one output AND gate. Because this is an OR term, this is the OR sign here, and there's an implied ANDing here, multiplication. Again, not really multiplication, actually just ANDing. Okay, so that's a simple example. Let's do something a little trickier. Let's do x, y, z plus x, y plus x prime z. What can we do here? Well, we should always look to see if we can use any one of the simplification theorems, S1, S2, or S3. Can we combine terms? Can we eliminate a term? Can we eliminate a literal? And I didn't go through these too much. I just talked about combining terms. In this case, we can't really combine terms, but one thing we can do is we can eliminate a term. So we want to use, if we go back to our theorems, we'll go back here to our list, and you need to become pretty familiar with this list. So here we're going to eliminate a term. That's S3. So notice we have xy plus x equals x. All right? So let's go back. All right? So now we have, we're going to use the term xy plus x equals x. Well, all right. So can you see anything where we have a term and then we have another term that's similar? And so let's let x be xy, and we'll let x be xy here. And so this is xz plus x. Oh my goodness, that just equals x. So that means we can drop that term completely. So now we're just left with xy plus x prime z. And we know from what we did up here, that's easy. We just use the C3, and now we get x plus z quantity times x prime plus y. So we used simplification theorem S3, and then we used C3. And most of our work when it comes to going through these problems involves exactly that. We typically have to use multiple theorems in the right order, and sometimes we have to just do some trial and error. But so here's some tricks that we'd like you to keep in mind. So here's some good hints. First off, you should write out the key theorems right here. Write out the two key theorems. You should make sure that you know which way you're applying it. So draw an arrow on top of the theorem and make the arrow point in the direction that you're applying it. So for instance, in this case, we were applying the second distributive law, and when we applied the second distributive law, we were applying it in this direction. So you should always, and then when we use the simplification theorem, we applied it in this direction. So you always want to make sure that you know which direction you applied things in. All right, the other thing we should do is we should use the simplification theorems first. Eliminate terms if you can, eliminate variables, combine terms, eliminate literals. And we'll go over some more of that. The second thing is if you're factoring, so which means you're going from SOP form to POS, you should always try C1, the first distributive law, and then try C3, multiplying and factoring, or C2, the second distributive law. On the other hand, if you're multiplying out, you probably should think about the second distributive law, or C2, and then the multiplying and factoring, or C3, first, and not think about trying to use the C1. And then if you do use C1, you're going to use C1 to distribute a variable into multiplied by a times a parenthesis. You're distributing it into there. And so that's how that would look. Let me just switch again and show you that. So for instance, let's say we'll make a little area here. So let's say you have x times y plus z. So the first distributive law lets us distribute the x in here, and that gives us xy plus xz. So this is when you're going from POS to SOP. That's where you would consider that. Okay. So we've proven a couple of the theorems. We've talked about the SOP and POS forms, and we've talked about how to switch back and forth. We've talked about De Morgan's laws, but we haven't shown you how to do take an inverse of a complete expression. So let's do that, and that will be pretty much the end of it. All right, so let's say we have an expression x plus y times z plus w, and let's say we want to take the inverse of the whole thing, which means now it'll, instead of giving us a 0, it'll give a 1, or if it was going to give us a 1 when it was evaluated, it'll be a 0. So that inverse is going to invert whatever the value of this expression is. All right. When we do this, this is where we do have to think about the order of precedence. So to apply De Morgan's laws, we notice all the operators. So we have an OR operator here, or a plus. Here we have an implied multiplication, or and here we have another plus. So we have to change these pluses into ands, and this and into a plus. So that's going to be x, y, quantity, plus z times w. Now, here's where it can get tricky. We really need to do this. Because we originally, this is a separate term from this, so we really need to treat this like these are in parentheses. And when we take this away, we could have xy plus zw. Well, that's different than xy plus z ANDed with w. So we have to keep this straight. And that's why you have to use lots of parentheses. So let's do it. Well, So in this case, we invert all the signs, all the operators, but we also invert all the variables. So now the x becomes x prime, the y, y prime, z, z prime, and the w, w prime. So we have all these primes that we didn't have before. Yeah. Mm-hmm. All right. So hopefully that shows you how to take the whole expression. Now there's a couple of tricky ones, and there's some that all the students struggle with. For instance, does x, what if we take the inverse of x times y? We invert that. What is that? That's x prime plus y prime. Now sometimes what students do is they'll think x, y quantity primed equals is the inverse of xy. But that's not true, right? That's not the inverse of this isn't equal to this. Well, I guess that is. But yeah. When we take the inverse here, we invert x, so we get x prime plus y prime equals the quantity xy prime. And what we don't want to be confused is to think that this equals x plus y, because that would be wrong. Okay, to do the dual, it's exactly like we just did it, only we don't invert any of the variables. We leave the variables alone. We only change the operators, and that's the dual. All right, with that I'm going to quit, and hopefully that will give you